Okay, in this video we're going to look at an example of a related rates problem. So, what's the problem? Suppose a stone is dropped into a pond causing circular ripples. Suppose we're given that the ripples have a radius which is increasing at a rate of 3 feet per second. And suppose further what we really want to know is how fast is the area inside the circle increasing the instant that 4 seconds have passed. How will we address this? How can we even begin? Well, let's start by labeling r as the radius at any given time t. So of course r changes with time, right? And so we really can note here that r is a function of time. So if we translate the given statement up here from English to calculus, it translates as dr dt is 3 feet per second. So notice up here I have the word increasing and at a rate in red. When you see anything about increasing or changing or rates, you're probably being told something about a derivative. And indeed, we're told that the rate of change of r with respect to time is 3 feet per second. All right, how can we translate the want to know? Well, first of all, we probably need to make another labeling. We're asking something about area, so let's let A represent the area at any given time t. And note, of course, A is itself a function of time, right? As time goes on, the area is changing. Now, I'll note here that usually when you think about area and the circle, you think of it as a function of its radius, right? We'll get back to that in a second. But how do we translate our want to know statement here from English into calculus? Notice I have fast and increasing here in red. When you see things like that again, you should be thinking, hey, I'm either being told or asked something about a derivative. And indeed, what we want here is the rate of change of area with respect to time, and at a given instant when t was 4 seconds. All right, so we've taken what we've been given and what we want to know, and we've labeled things like r and a. And we've even translated our given and want statements from English into calculus. How do we proceed? Well, notice I mentioned that A is a function of r. And of course, I think we probably all knew that, right? That the area is pi r squared. But let's look at this equation. Recognize here A on the left is a function of time. And so over here, if r is a function of time, this all can be considered one big function of time on the right. So let's differentiate both sides with respect to time, giving us the following. Well, the derivative of a with respect to t is dA dt. That's what we mean by it. And if we look at the expression pi r squared, that's a chain rule, knowing that r is a whole function of time. So the pi goes along for the ride. That's a constant multiple. Then the chain rule has us take the 2 out front. The new power of r is 1. And of course we multiply by the derivative of r with respect to time. So that's our chain rule. Well, hey, you know, we know what dr dt is. We can plug 3 in for that. So we're getting there. We want to know a value for dA dt, and it looks like we're only down to, could we plug something in for r? If only we could substitute something in there. Well, actually, after 4 seconds, the radius has been growing by 3 feet for each of those 4 seconds, so it's up to 12 feet, and so we can substitute 12 in for r. So 2 times 12 times 3 times pi is 72 pi. Now one other thing, the 3 here was, if you remember, in feet per second, and 12, that's a radius, that's in feet, so we end up with feet squared per second. So what we've learned is 4 seconds into these ripples growing, the area inside the circle was increasing by 72 pi feet squared per second.